All right. If you hear music in the background, I didn't add it to the video. The bar across the street is playing some, and what can you do? So, this is the third episode for Shader Dev Series, 3D Graphics for Games. And this is the third episode, and probably next to, if not the last, Math Primer episode. I know there's been a lot of this stuff, but like I said, if you want to get into shader programming and you haven't at least gotten yourself familiar with these concepts, you'll be lost day one. So today, just a recap of stuff we talked about. Watch the other videos if you haven't seen them, where I covered vertices, vectors, polygons, planes, and angles. Today we're going to talk about coordinate systems, which are huge, and transforms, which are huger in importance for shader development and 3D graphics in general, and really, in some cases, 3D, well, yeah, in a lot of cases, 3D game programming in general. And then after that, I'm going to get something to eat because I'm getting hungry. So, basically, we are going to be talking about a number of coordinate systems, and these are all Cartesian, meaning that they're not weird, affine, skewed, strange coordinate systems. They're just straight normal coordinate systems that you would expect in 3D, where, you know, X, Y, and Z are all straight orthogonal lines. So, like I said, not a mathematician, but the way I define a coordinate system in my mind is that it's defined by an origin, which is the XYZ point zero, kind of the origin or the zero of everything, and three orthogonal axes. And orthogonal is just a fancy word for perpendicular, meaning that all three axes are all right angles to one another. Another way to think of this is the corner of a perfect cube. You know, it has three axes shooting out of it. They can be rotated any which way, but they have to be all 90 degrees from one another. So we're going to talk about today the most commonly used OpenGL coordinate systems, because that's what this video series is aiming towards. And by OpenGL, I mean Direct3D 2. I just mean 3D graphics, ones that shaders will work with. You know, we're going to be working with coordinate systems that are relevant to 3D shader programming. Certain ones are going to come up a lot, like all the time. So the first one I want to talk about is called world space, and this is the space that you're commonly used to thinking about and working in when you're working inside a 3D editor like Verto Studio or Maya. Essentially, it's a 3D coordinate space, and it's the space where you position all your objects in. So you have your x-axis going across, your z-axis going across the x-axis, and then your y-axis is straight up and down. That's your standard world space. There really isn't much to say about it except that it's kind of a place to keep yourself grounded when we get into some of the ones I'm about to talk about, because there seems to only kind of be one world space. There's only really one origin, which is that zero that is kind of the center of your whole scene. The other coordinate systems I'm about to talk about, there can be many of these to think about. So there's object space. The way to think about object space is that it's a local coordinate system to a specific 3D object in your scene. So in the case of this ring, the origin of this ring is actually the tip of that sail. It's the point that's basically the center. Object space usually has the object centered in that space. So the origin is the center of the object. That's not always the case, but that's usually what you'll want to do. And that's really what I can say about object space. It's basically a local coordinate system for each individual object. Every object defines its own center and its own object space. And when you're editing vertices and working with them, they're commonly stored in their own object space. And this makes it easier to do transforms on them, which I'm going to get to. View space is another important space. This is basically the space defined by the camera or the viewer where you're looking. In this space, you can think of your eyes are the origin. So the actual viewer defines the origin, the point that is looking as the origin, and the axes are essentially fixed to to your eye. So like if you were to hold your right hand up to your eye and make an L shape, almost like you were calling yourself a loser, um, your index finger would shoot straight up. That's the y-axis. And your thumb makes the x-axis. And basically, what this means is that in view space, x is always going across the side and y is always going across the top, very much like a computer screen. And this is a useful space because sometimes you want to know where objects are relative to the viewer, and sometimes you want to know how far out they are. So, for example, z is always going forwards from you. And OpenGL is actually the negative z-axis that is going away from you. But it's basically there's a way to move into the scene, and as the camera moves around, these axes of view space are always aligned to the camera. So it's a really useful space to work in when you want to find out things that the user or the viewer may or may not be able to see. You can use view space to determine that. So that's view space. Screen space is very similar to view space, except it's post-projection. So I haven't really talked about this much, but when you're working in computer graphics, the computer is working with coordinates that are in 3D, but they need to show it on a 2D computer screen. And the way that's done is with a projection. Basically, you project those 3D points onto the 2D screen. And the space that you're in as a result of or after this projection is called screen space. And basically, it's a normalized coordinate system. And what I mean by normalized is that x goes from 0 to 1, and y goes from 0 to 1. And z, even though you think of screen space as being two-dimensional, z is still given to you. It's just shrank in the range of 0 to 1, where 0 is right up at the viewer, and 1 is all the way out at the what's called the far clip plane. And the z information is really only needed for z buffering or depth testing to determine which polygons and pixels are in front of one another. But basically, you can think of, with the exception of that, screen space as kind of a two-dimensional space. It's basically the result of projecting the 3D, projecting this space, view space, into screen space. It's kind of a mouthful. Texture space is a more interesting space, or one that I didn't want to leave out. Texture space is essentially it's sometimes called UV space. It's a 2D space. And basically, your points of your mesh are defined in this space that's used for texture mapping. So, for example, when you open up the texture coordinate editor in a 3D Studio program, you're basically viewing your surface in texture space, and you're able to move it around and affect how the texture mapping is done to it. And it's also a normalized coordinate system, meaning that u, which is kind of like the x-axis, goes from 0 to 1, and v, which is like the y-axis, goes from 0 to 1. And 1 usually corresponds to the full width and height of the texture image. So that's texture space. Surface local space is interesting, and it's commonly not thought about because it's kind of a more arcane concept with respect to the other spaces. Surface local space is you can think of as similar to object space, but instead of having every object have its own little local coordinate system, every vertex, or really every possible point on the surface, has its own coordinate system, where the normal is kind of the vertical that shoots off the normal vector, and then the two other vectors that are perpendicular to that normal that define the little three axes make up the tangent and binormal, which are basically used to traverse along the surface. So you can think of it as if you were like a small little ant or a bug or an alien or something standing on the surface. You would basically be in that surface local space. And this space isn't used that much, but it's critical for effects like bump mapping and some of the more advanced shader effects that need to determine things, features of a surface without just the normal. It needs those other two vectors. That's what surface local space is for. I feel like I was going to say something else about this, but I forgot. I'm probably going to just leave it at that. So that's surface local space. Oh, I was going to say that, even though I'm only showing those axes at every possible vertex, they're really defined at every single pixel or point along the surface because they're interpolated between the vertices. And I'm going to cover that when I talk about the shader programming in more depth in the other videos. All right, so that's coordinate systems. There's a lot of them. You don't feel like you have to memorize them, but if you do enough shader programming or enough 3D game programming over time, you're just going to know them. So what are transforms then? So transforms are a very general concept in 3D math, but we're only going to talk about the ones that are useful for game programming. They're a facet of linear algebra, essentially. So there's a couple of types of them, and I'm going to go over the most common ones. Translation, I have no idea why they didn't just call it moving, but translation is a fancy mathematical term for moving something, just moving it around or shifting its position. Rotation, which can be done about any axis in 3D space. And scaling, which scales something. And then this one I underline because it's kind of where everything's going to conceptually. You can transform or convert between coordinate systems with a transform as well. All right, so how are transforms done? They are done by basically a matrix multiplication. Now, someone's going to see all this math and get frightened immediately. Matrices tend to scare people away, and they did when I first saw them too. And the reason why I didn't fill that matrix in right now is A, B, C, D. It's kind of whatever. You can think of matrices as like functions that do transforms for you. That's basically all they are. And you can accomplish a transform by basically taking a point or a vertex or a vector and multiplying that point by the matrix, or multiplying the matrix by the point on the left-hand side. And that's how you do a transform. It's basically a matrix times a vector multiplication. And to do it on a mesh or an object in 3D space, you just multiply each vertex in the mesh, all of the points, by the same transform matrix, and essentially you've transformed that object. So if you have like a sphere or a torus or a sailboat or whatever, the way you transform that 3D object is you generate your transform matrix, and then you multiply that matrix into every single point of the vertex, like in a for loop or something, and that's it. The reason why I don't want that math to scare you too much is because the math stuff looks bad, but in GLSL or shader programming, it's actually really simple. If you have V4, which is your point, your vector, and you have mat4, which is your matrix representing your transformation, you just do m times V4 and store it back into V4, and you've transformed your point. It's that simple. It's basically one line of code, because matrix multiplications are built into GLSL. You don't have to know how to do them. I still don't have it memorized in some cases. So that's how a transform is done, but that's not too useful if you don't know how to at least generate some simple ones. So first thing I want to talk about is why is the matrix 4 by 4, and why are we using vec4 instead of vec3? Why is there an XYZW there? The short answer is, remember, this is a primer. It's not going to go over every possible concept because we'll be here forever. And you can look this stuff up if you're really interested in it. But for the sake of game programming, it's basically needed to allow translation or movement to be done in a matrix. That's a short answer. And it's needed for perspective projection magic to work. It's just a mathematical hack that somebody put together to allow one type of matrix to do all your transforms for you. And they decided that using a 4x4 and a XYZW four-dimensional point was the way to accomplish that. And it actually gets even simpler when you think that the input vector, basically the vector that you use for V4, XYZ obviously comes from just your point, but W is 1 if you're transforming a point, and you make W 0, the last part of the vec4. You make that 0 if you're transforming a vector. And the simple reason why, I'm actually going to get to that in the upcoming slides, but that's the general rule of thumb. So the first matrix that I'm actually going to show you guys, and like I said, don't worry too much about what these matrices look like. I just felt like I should at least show you a couple of them. You don't have to memorize this. You can look this up really easily, and it's almost, for 3D game programming, there's so many libraries out there. Hand constructing a matrix just almost never happens. You don't have to worry about it. So represented by capital I is usually the identity matrix. If there's one matrix you should actually care about, it's probably this one. This matrix essentially does nothing. If you multiply a point or a vector by this matrix, it'll be as if you didn't do it at all. It has no effect when it's applied, and that's common. That's why you commonly will see the word identity matrix as kind of the initial state for maybe a transform when someone's using it, because they just want to put a placeholder in there that says, I haven't done any transforms in this matrix yet, just leave it as I, basically. And that's basically just ones along the diagonal and everything else is 0. Translation matrices are very similar, except you'll notice in the upper right hand side, or the last column of the matrix, there's delta x, delta y, delta z, which are basically the deltas, the amount you want to translate or move the object by, and that's what that matrix looks like. It's important to note, and this is why I said I was going to explain this, this has no effect on vectors. So if the vector that you're multiplying this matrix into, if w is 0, the translation won't have any effect. And that's for good reason, because vectors, remember from the earlier video, vectors don't represent a position, they only represent a direction. And if you were to translate the vector's direction based off of this translation, you basically would screw it up. So you don't want to do that, and if you make w 0, that's taken care of for you automatically. I basically just said this. This is called translation when you move something. Scaling, basically, I messed this slide up. That D should be 0. I don't know why I have a D there, but basically it's zeros everywhere except the diagonal, and then on the diagonal SX, SY, SZ, and then 1. And SX, SY, SZ are the scaling in X, Y, and Z. And they're commonly all usually equal to the same number, unless you want to do a non-uniform scale. So if you just want to scale everything and by the same amount, you just basically put the same number in the diagonal, and you leave that last one 1, and you have your scaling matrix. This is important to note. So when you scale something with the scaling matrix, the scaling always occurs from the center, or from the origin of the point. So if the point is, if it's around 0, it'll scale away from 0. So for example, I'm assuming that star is centered before I do that scaling transform on it. That's an important concept. Rotation, I put ... in here because there's no reason for me to show you what a rotation matrix looks like. There's sines and cosines in different places depending on what vector you're rotating about. It's just not necessary. I've been doing 3D programming for many years. I still haven't memorized what a rotation matrix looks like because I always just look it up or have some function call that generates it for me. There's no need for me to show it. And if you're really curious, you can go look it up yourself. But basically what a rotation matrix does is it rotates the vertices around the origin, again, around the center. It always assumes things are centered. And I'm going to explain later why that you can get yourself into trouble, or you should know what you're doing if you do a rotation where something's not centered first. All right, so order is important. This is an example of why order is important in the order that you apply transformations. So here's some GLSL code that essentially will apply 2 transformations one after the other by doing a matrix multiplication. Remember, to apply a transformation, you just do a matrix multiplication. So there's a vec4 called post, it's my position. There is a mat4 called translate and a mat4 called rotate. Translate is a translation transformation and rotate is a rotation transformation. So if I do first position equals rotate times position, I'm rotating it first and then I'm translating it. This will happen. It rotates first and then it translates. And the result is, obviously, if you do this in one shot, you're just going to see a rotated object where you put it. Basically, if you have the position set, you put it where you want, and if you have the orientation or the rotation set, it'll rotate it, and it'll just basically be a rotated object wherever you want to position it. Now, if you reverse the order of that, something interesting happened. So note here, I've done it in the reverse order. Now I'm translating it first, and then I'm rotating it. So what happens is it translates. Keynote is not able to do rotations that are not around their center, so bear with me here. Basically, now that I've translated it, but I want to rotate it, it's not centered anymore. The center is where the old gray star is. So when I go to rotate this, instead of rotating around its own center, it's going to rotate around the origin, and it's basically going to revolve. And the end result is going to be something like that. And that's why it's important to keep in mind the order of your transformations when you're applying them. Transformations are also composable. That's a really, really important concept that's actually really awesome. So basically, if you have the same example I had from the first slide, but instead of applying the result with two matrix multiplications, one after the other on posts, I compose the transformations into a mat4 called final. So basically, I'm actually multiplying, translate, and rotate. I'm doing a matrix multiplication, which of course GLSL does for me, of translate and rotate, and it composes both of those transformations, and now only one transformation is needed to post. So basically, this would be the same as if I did translate times rotate times position, or final, the transformation denoted by final, is the same as if I did one after the other, but it does it in one shot. This is a really, really neat idea because you basically can take as many transformations as you want and compose them into one matrix, which will do the thing in just one multiplication, which is really cool. So bringing it all back to coordinate systems, we've talked about translation, rotation, scaling, but we haven't really talked about how to convert between coordinate systems. So this is what's really neat. Just like I talked about, a single transform can get you a series of translation, rotations, and scales. A single transform can get you from any linear coordinate system to any other in one shot. You can convert between them just like that if you have the right matrix, and that's really cool. So that means you can take a vertex in model space and transform it all the way to screen space where it's supposed to go on the screen with just one matrix multiplication. It's just one transform. So that's really cool. Like, the ability to do something like that means it greatly simplifies just about everything I've taught you guys in the last couple slides. In other words, this is the main job, or one of the main jobs, of a 3D shader. It basically takes a vertex, which is part of a model or a 3D model, which is in model space, does a series of really just one matrix multiplication for the simplest case, and gives the answer back for where it should go on the screen. And that's it. It even gets better too. These matrices are usually passed to the shader as an argument. You seldom have to compute them yourself in a shader. They're computed for you, usually by the OpenGL program that's running the shader. Now this is where you guys can get a little happy. If you're using a shader building system like Verto Studio or Unity, the matrices, fantastic. The matrices are computed for you in advance and just handed to you. So in other words, if you're doing shader development in Verto Studio or another shader production system, you don't ever have to compute these matrices yourself. They're just given to you, and you can use them to do the transformations as you see fit because they're there for you, which makes shader programming a hell of a lot easier than full-on OpenGL programming. It's one of the reasons why I like it. It's just simpler. So that's basically the end of this primer. The next video is going to be still slides, but I'm going to finally start talking about the job of a shader and how vertex shaders work. And we're going to really start getting into shader development now. So I'm excited. Thanks for watching, guys. More videos coming.